Because he wants to be like correct with COVID, but it's not really, because they can't get anybody to fill up a room.
Today, Joe Biden and his family attended Mass in Delaware. His campaign getting a major cash infusion.
Wait, Sarah, is that coming from your computer?
Committed.
Okay, there we go. Hello, everybody. Why are all your cameras off? Come on. Hey, we got some people. Hello, Aiden. Hello, June. Only 3 cameras? Come on, that's fat. Let's go. We need to make full camera shit. Let's go. Is eating allowed here? Yes, it is. Okay, today we're probably gonna split things up so that we don't have everybody in the same room, so that you guys feel a little bit more comfortable asking questions and stuff. So, right now, how many people are in silver or above or want to like go to the advanced side? Because basically we want like silver people in one room and then everybody else will be here. So raise your hand in the participants thing if you are silver or above and use go. Only one? Anybody else? Okay, we'll see. We'll wait for a little bit more people to come and then. Hello, we got some more people. Noise. Hello. And another one. Once again, ideally, if you guys could turn on your cameras, please do, because that would be much appreciated. Of the new people who joined, how many of you guys are in silver or above? Because if you guys are, I'll put you in a different room. Okay, okay, so 2 of the new people who came are in silver, so that's looking good. Yeah, feel free to put your hand down.
What's the difference between this room and the other room?
Nothing. We're going to go through the same presentation.
Wait, what's the difference?
Yeah, there's no difference. It's just we're going to go through the same presentation, except if you're in silver or above, they'll probably go through things faster, and then you'll have more time to work on the problem and stuff. So, and then obviously, like you could ask more complicated questions, but like in this room, I'll go a lot slower. So for people who are new, it should be better. People are still trickling in, so we will wait a little bit more. Okay, let us make some breakout rooms. Hold up. Okay, we're probably going to start right now. So once again, right now in the participants thing, go and raise your hand if you are in silver or above, or you want to go to the advanced room. And then I'll put you there. Okay.
Did you say silver and above?
Yeah, silver and above.
Silver and above in what?
In Yusuko. Or even if you just want to go, if you think you are ready, feel free to let me know and I will put you in the other room. And then let me put the officers in there too.
Wait, who's the officers in the advanced room?
Everybody except me. I'll stay here, and then the rest of you guys will go in there.
I'll stay in this room with you then.
Oh, okay.
All right.
All right, so let's get started. I'll open the room. So if you guys got the thing, go ahead and join and we will be good. Okay, so I hope you guys are ready because today we are going to be talking about array searching and sorting. So feel free to ask any questions you guys might have. Hopefully you guys are more comfortable with less people in the room and that should be good. Lisa, well, when she comes online, I will ask. Wait, Lisa, are you silver or above in Yusuko or?
No.
Okay, so then this is the right place. Okay. So today we are talking about searching and sorting. So basically, does anybody know what an array is? How many, like, raise your hand on participants if you know what an array is. You guys better know what an array is. Come on. No, I'm kidding. Okay, so basically what an array is just a way of storing numbers, okay? So this is just a bunch of random info. We're gonna get more in detail, okay? So essentially what we're gonna be talking today is about arrays and array lists and the cool algorithms that you could do on them, okay? So the first thing is arrays. So if you, how many people code in C or Java? Okay, so I think most of you guys code in C or Java, right? So basically in C or Java, you could have these fixed size arrays. And that means that you set aside some amount of memory and you could just access elements, change the elements, whatever, but it's always fixed. You can't change the size of your array. But there is also, does anybody know what the variable size arrays are called in C++? Feel free to unmute and tell me. Come on, anybody. Variable length arrays in C++. Come on, please. Anybody? Okay, well, they're called vectors, okay? So vectors are your variable length arrays, and does anybody know what it is in Java? I guess not. It is array list. So basically, in Java and C++, you have the variable length arrays, and this is the same thing in Python, right? Like your lists are all just variable length. You could add to them, you could subtract from them. There's no fixed size. And basically the way they work is you have some capacity, and then you have a certain size, it keeps track of it, and whenever you add to the end, it moves the end over so that you have more space. And if you get above the capacity, it just doubles the capacity, so you could store as much stuff as you want. So basically, both of these have their uses, right? Like, for example, if you want to store like 1,000 numbers and you know you're always going to have less than 1,000 numbers, you would use an array, right? Because then you know how much you're going to have, so there's no reason to have like variable space. But if you don't know how much you're going to have, then vectors are probably like the option you want to go with. Okay, so I don't know whether this will be particularly useful. Does anybody like not know how to code arrays in like their language? I mean, probably if you guys did the HackerRank thing, you probably know how to use arrays, so I'm probably not going to do this. Okay, so now, the most simple example of an algorithm on an array is to swap it, right? So could anyone tell me the like easiest way to swap an array?
Swap opening parentheses A comma B closing parentheses.
Nice. Okay, true. Albert, why are you in this room? Let me move you to the other room because you are an advanced boy. Okay, hold up. Why are people still joining? God dang it. Hold up. Give me a second. Breakout rooms. Assign to. If you guys have a question, feel free to just ask it. Okay. So you guys can still see my screen? Okay. So can anybody tell me how to swap an array? Like how do you reverse the array? Anybody? What's the most easy way to do it?
You have a temporary array and then you run through from 1 to 0. No, you run through backwards as a for loop.
Yeah, exactly. Literally, you just go 1, copy it over to the last place in the new array, take 2, copy it into the second last place in the array, and so on and so forth. And then eventually you got your swapped array. But what is the problem with this? Why is this not ideal? Could anyone tell me why it's not ideal? What do we have to do that is not good? Anybody?
You have to replace the previous one, so you can't access it anymore.
Well, yeah. So, okay, let's say that we didn't make a temporary array, right? Then, like, if I move the 1 to here and overrode the 7, then we don't know what the 7 was, so that's bad, right? And
You
then
make,
like
like-
how we move it over. So yeah, so Aiden, what were you saying?
You can like make like a holder variable. So you like hold the value at position 6, and then you swap it and you swap it over.
That is what we are going to do. But what is the problem with your approach, Aiden? What is the problem with creating a temporary array?
Well, no, you make one variable to store the value.
Yeah, I know. But like, what was the problem with your, like, what's the problem with making a temporary array? Why do we not want to make a temporary array?
It takes up a lot of space.
Exactly. You basically had to store twice as much memory. Why would you want to do that? So essentially, we're going to use a smarter way, and basically what Aiden said, right? Like Rushil said, if we move the 1 to the 7 spot, then we're done, right? Because we don't know what the 7 is. But if we store it in a like temporary variable, we like say x is equal to 7, move the 1 in there, then we can set the 1 to 7, and we are good. We didn't have to make any more space, and all we had to do is swap those two, and then we just swap each one, and we are good. So you can see they take 1 and 6, they swap it, you got 6, 1. Then you take 2 and 4, you swap 2 and 5, you swap that, and then so on and so forth. And basically the reason why this is good is because you don't have to add any more space, right? Now, here's a more complicated example using arrays, okay? So let's say we have a sorted array and we want to find the pair of distinct elements whose sum is closest to 15. Could anyone tell me which pair it is really quickly? Even for a human, this is pretty hard, right? Anybody, tell me which pair of elements is the closest to a sum of 15?
-3 and 17.
Yep, and there also happens to be one more. Anybody else? One more.
19 and -3.
Exactly. So there's literally like two options, but even for humans, it takes a really long time to do this. But so what is the brute force way of doing this? Like, if we didn't want to think at all, how would we just solve this just by using a computer, do it a brute force way? What's the brute force solution?
We compare like every variable and record the sum.
Yeah, you literally just go through every single pair. You have a for loop, -9, and then you for loop through the rest of them. -9 plus -7, -9 plus -3, -9 plus 0. And then you move on to -7, -7 plus -3, -7 plus 0, and so on and so forth. But you guys can see why that's so inefficient, right? Because like, obviously, -9 plus 79 is gonna be way too big. So obviously you want to shrink that, so you'd have to move over, right? But basically we're doing a ton of extra work. So, okay, first off, what is the O of n runtime of going through all pairs?
N squared.
Yeah, n squared, right? Because you're literally going through every single pair. But we could be a lot smarter about this. So essentially we have the two-pointer approach. So essentially the two-pointer approach relies on the fact that we start at the ends, and what happens if I move the pointer right? Does the sum increase or decrease? It's a sorted array. Yes, go ahead, Rushil.
Increase.
Yep, it increases. What happens if we move this pointer left?
Decrease.
Yep, so right now, what is our sum, and do we need to increase or decrease?
Decrease.
Yeah, we had a decrease, so we moved the right pointer left, right? So now we have our pointer, and our best sum is 17, but we want a 15. This sucks. So now, which pointer do we move and where? It's too big, so that means we got to reduce our sum. Which pointer do we move?
The one under 56.
Yeah, so now we move it to 41. Then what do we do?
29.
Which pointer do we move and where?
Right side.
Say it again.
Right side.
Yeah, you move the right pointer left again. And we keep doing that until now, over here. We have 19 and -9. Now what's our sum, and which pointer do we have to move?
The left one.
Yeah, because our sum is too small. 10 is less than 15. But it's equally as good as our current best sum, which was 20 when we had 29 and -9, so we added to our best sum. Okay, so now what do we have? We have 19 and -7. This is too small, but it is better. It is closer to 15 than both of our best sums, so we update our best sum to be, well, what do we update our best sum to be? What's the closest sum we have so far to 15 now?
12.
Yep, we updated to 12. And then we're now at 19, -3. Now what's our best sum going to be and which pointer moves where? Okay, first off, what's our best sum after this move?
16.
Yep, and which pointer do we move and where?
I mean, I guess that's the closest you can go at this point.
Yeah, but the computer doesn't know that, right? So what should the computer, which one do they move? And let's say we wanted to find all of the best sums, right? Because
The
there's
right
another
one
one in
to-
there that we want to find. So say what?
The right one to 17.
Yep, and now we found the other one, right? We found -3, 17, which is 14, which is equally close. We found both sums just by doing this algorithm, and then the rest of it, you guys know what happened. So essentially, just by being smart, we were able to reduce the amount of work we have to do. Does anybody know the runtime of this?
N log n.
It is n log n if it's not sorted already, but assume that it's sorted, then what is the runtime?
Order on.
Yeah, it's O of n because literally the pointers only have to go, they never go past each other. They only have to like see each element of the array exactly once. So it's O of n. So essentially we were able to speed this up a ton just by being a little bit smart about it. I will code this up in Python if we have time at the end, but for now, let us move on. So now you saw that like just by having a sorted array, it helps us sort problems, but how does it actually work? So basically the first sorting thing, the first sort that we got to talk about is selection sort, okay? So essentially, it basically, the concept is it takes the minimum and puts it at the front. So what number here should go to the front first?
1.
Yep, 1 goes to the front first. Now, this part is sorted. The rest of it is what we care about. Now what goes to the front?
2.
Yeah, 2 goes to the front. So you swap 2 and 4. You can see this is a 4 now. 2 is at the front. You still have this part is sorted. Then what goes next?
4.
4 goes here, right? Then 5 goes in, right? Then what goes next?
7.
Yep, 7, and then 8 goes next. And hooray, we got a sorted array. So this is basically one of the simplest algorithms out there to sort a thing. What's the runtime? Sorry, I didn't hear you. Yeah, n squared. Could you tell me why though?
Because each time you have to run through the entire thing at like.
Yeah, so you can see like
through n numbers n times.
Yeah, exactly. So like the first time we had to run through the entire array to find out what the minimum was, right? So we found 1. Then we put 1 to the front, and then we had to run through the rest of the array a whole nother time just to put 2 at the front. And then you had to run through the entire array to put 4 at the front. So clearly this is not like a very good sorting algorithm, but it's the simplest one we know. Okay, then there is also insertion sort. So basically what this does is basically what happens. Okay, so you start with this unsorted array, right? And basically you start with 3, and if it's less than 4, you move it left. And then now 3 and 4 are sorted, so they're sorted now. Then 2 moves left twice because it tries to get to wherever it's sorted in this red stuff, right? So the reason why doesn't 10 move? Could somebody tell me why 10 doesn't move at all?
It's bigger than 4.
Yeah, so it'll only move left if it's smaller, right? It wants to get sorted in the red part. So if it's already sorted in that like the beginning part, there's no reason for it to move. Same at 12, but then 1 is clearly the smallest of all these numbers, so it moves left. Oh, I'm less than 10. Oh, move left. I'm less than 4. Move left. Oh, I'm less than 3. Move left. Oh, I'm less than 2. Let's move left. So essentially, it basically just keeps moving the stuff left. I have a good example video for this. Okay, so could anybody tell me what the first thing that's going to get swapped is? So we start at 35, 35 doesn't change. What happens to 97?
It stays.
Yeah, it stays because it's not less than 35, there's no reason to move. What happens to 19?
It moves to the left.
Okay, it moves to the left, now it's here, then what?
It moves to the left again.
Exactly, so now this part is sorted, right? Let's get to that part of the video. Whoops, I went too far. Right, so now you have this green part is sorted, then what happens to the 4?
All the way to the left.
it moves all the way to the left, right? So now we have that, right? Then 57, where will the 57 go?
To the left
How many times?
once.
Yep, exactly. So basically you guys get how it works. You just keep moving it to the left, you keep moving it to the left until it fits in. This one doesn't move at all. Then 36 will move all the way over here. And then eventually our array is sorted. Amazing. So that's how insertion sort works. Does anybody know the runtime of this guy?
N squared.
Yep, I mean, it's kind of on the side, but basically the idea is, right, like, okay, you see how like one had to go through like all of the ones before it? What happens if our array was perfectly flipped, right? Then each one will have to go all the way to the front. So essentially, that's like, basically you had to move it n times each time, so that's like n squared. That's why this one's also not that good. But we get to even better type of sorting, merge sort. So basically the way it works is you just divide each half and then you sort each half and then eventually you want to merge them together. So you can see, right? Like we divide it up, we divide it up, we divide it up. So how do we like, let's say that we have two sorted arrays. Now the clever part is how we merge them together. Assume that we have two sorted arrays, how do we merge them together to make one sorted array?
2 pointers.
Yep, it is a 2-pointer thing, exactly. Okay, so basically we start our pointers. Let me actually make some arrows here. Actually, that's probably not a good idea, but our pointers start at 3 and 9, right? And which one is smaller, 3 or 9? Anybody? 3, right? So we put 3 first, right? Okay, so now which pointer moves and where? If we have our pointers at 3 and 9, which pointer moves? Anybody? We already took the 3, so now which pointer should move? Come on, people. Well, okay, so
left.
yeah, the left pointer moves to the right because we already took the 3, and now we're at 27 and 9. So the smaller one is obviously 9, so we take the 9, and then which pointer moves? Anybody? If we take a number, which pointer moves? Nobody? Okay, well, basically your 9 pointer will move to 10, and now you're looking at 10 and 27, and then you take the 10, and then you're looking at 82 and 27, so you take the 27, then you're looking at 38 and 82, you take the 38, then you look at the 43 and the 82, and you take 43, and then you finally take 82, and hooray, you get the last number. So basically all you got to do is you divide it up, and then you keep merging these together. Because like this right here, if you have one of each element, they're basically all just sorted, right? One thing by itself is sorted. So if we are able to merge them, then we could sort the array that way. Okay. Quicksort's kind of complicated, but basically you just choose a pivot. You decide which ones are greater than it, which ones are less than it, and then you just do the same thing for all the other, like you just keep repeating the same process. It's kind of complicated. If you guys want to search it up, feel free to. Then there's a bunch of other sorts, right? You basically have like bucket sort, which basically like, okay, let's say your numbers are confined to 1 through 10, right? How could we sort that without actually having to compare the numbers to each other? Any ideas? Well, we could, yeah, go ahead, Rushil.
Divide into categories like between 0 and 3, or between 4 and 6, like that.
Well, in this case, we could straight up just do 1 and 10, right? Like it's equal to 1, it's equal to 2, it's equal to 3, it's equal to 4, it's equal to 5, it's equal to 6, it's equal to 7, and so on, right? Like we could store how many are equal to 1, right? Then we can store how many are equal to 2, and so on and so forth. And then how do we reconstruct the sorted array from the numbers, right? Let's say we have 2 1s and 3 2s. What is the sorted array? Anybody? Come on, just like x comma y comma z. Please, if you have 3 1s, 2 2s. Anybody? Well, it's literally just 1 comma 1 comma 1 comma 2 comma 2, right? All we had to do, count the number, and we already know what the sorted array is. That's basically how bucket sort works. Radix sort is basically the same thing, but yeah. And bogus sort is a best sort there is out there. Basically just try all permutations and hope that one is actually sorted. Kind of big brain. All right. So here's a very fun sorting visualization. Like this is probably one of the best ones I've seen. Let me present and then click the button. Okay. So you guys can see this, right? So this is selection sort, right? You're basically finding the min and you move it to the front. Then insertion sort, you just keep moving the ones to the right position, right? You keep moving them into there. And eventually you get a sorted array, right? That's what we saw before. And then the next sort we're going to see is merge sort, I'm assuming. Quick sort. So you can see that it like sorts individual sections and it keeps splitting it up into like somewhat sorted parts, and then eventually it smooths out each part, right? And then merge sort, you can see it's dividing it up into two. It goes from left to right, and then it combines the two every time it finds it completely sorts something, right? There's a bunch of like cooler stuff too. Basically heap sort, it just puts everything in a heap and then just take the smallest one each time, basically. So that's cool. And then radix sort, that's cool. Well, let me see if there's another fun one. Do they have bogus sort? Oh, bubble. Yeah, okay, yeah. This one's pretty fun. So basically each one just bubbles around until it finally just luckily ends up. That's why they put less stuff. So it's kind of cool. There's a bunch of really funny ones.
There was like a BOGO sort one, except it was like really small. It was like 8 test cases or something.
Yeah, you can't do it. Yeah. It's like n factorial, right? If you go any bigger than 8, then you're screwed, right? I don't know what half of these are, but it's pretty good. Oh, there you go, BOGO sort.
Wait, this one thing takes a while.
Yeah, okay. Wait, did it actually find it?
No, it doesn't.
It doesn't ever find it? Wait, that's kind of sad. Yeah, you can see that it's just going forever. Oh, yeah, okay. So basically, bogus sort sucks. Okay. All right. So now we're going to talk about the last cool array algorithm that we probably could talk about because we're almost out of time. Binary search. So essentially, let's say that we're searching for 16, right? Or no, let's go with something fancier. Let's say we're searching for 5, okay? And it's a sorted array. So essentially what we do in binary search is we look at the middle element. So 16, let's say. So now, do we have to go up an array or down an array to find 5? Yeah, so essentially we know that 5 is less and this array is sorted. So that means it has to be in this side. If it can't be in this side because all those numbers are greater than 16 and 5 is not greater than 16 incidentally. So we look at only this part. And then we repeat the same process. We look at the middle element. Which way do we have to go now? We're looking for 5 and we're at 8. Which side do we have to look on? Come on, it's not that hard.
Left.
Yeah, we got to look on the left. So we look at these 3, we look at the middle, and we found 5 in like 3 steps, okay? Pretty big brain. Like, of course, you could be a cool kid and just go through it until you found 5. But what happens if it's at the end? Then you had to go through the entire array to find it. So essentially, does anybody know what the O of whatever log? I mean, the O runtime is of this algorithm?
Log n. Log n.
Yeah, log n, right? Because you're just dividing it in 2 each time, so it's just log n. I probably should have showed you guys a slide, but you guys got the idea. Okay. So essentially, it's pretty useful in competitions. You'll probably get a lot of experience doing that if you get into like silver or something. But does anybody know what this code does? So essentially what it's doing is you have your binary search, right? So you start with the left and the right, right? And then you find the middle and you check if this function of m is less than 0. If that's true, then you move left up, and otherwise you move right down. Can anyone guess what this does? F could be literally any function. Well, basically what it does is it finds the smallest number such that f of m is a positive number, right? Because it basically checks if it's less than 0, move it up so that until we get an m that actually results in it being greater than 0. So today we have a challenge. I don't know how much time we have, but basically if anybody manages to solve it in 4 minutes, then you guys get a winner flag, but otherwise I'll just give you guys the meeting flag now. Thank you guys so much for coming. But yeah, if you guys could work on that, that would be great. I will give you guys a meeting flag. Let me stop sharing real quick. Do you guys have any questions though? That is the real question. Like on the competition website, we have a bunch of use of code problems, a bunch of practices. If you guys want to practice this kind of stuff, because basically the challenge is on the competition side. So if you want to practice, go check it out there. Let me send the meeting flag. Hold up. Okay. So if you guys want to take the meeting flag, submit it. Here it is. And we are done for today. So if you guys have any questions, feel free to let me know. Otherwise, if you guys manage to solve the problem, like in the next 10 minutes, I would be happy to give you guys the winner flag. But other than that, you guys are free to go. So see you guys. It's on the competition website. Basically, it is 2.2 for you, Brian. But if you're a novice, then 2.1.
Wait, where is the website? What?
Oh, let me send you the link, ctf.shscsclub.com. There you go. Yeah, feel free to drop out if you guys are done. If you guys are trying to solve the problem, then I will wait. So, Brad, is that a hand or that left over? How many of you guys are actually working on the problem? I guess not many.
Not many. I'm opening Zoom for my
Okay.
period class.
Okay, yeah, you guys have 7th period. All right, then I'll just end the meeting then. Wait, are Isha or R&J, are you guys working on it?
R&J also has 7th period.
Oh,
I'm
okay.
getting in Zoom class, yeah.
All right, yeah.
Okay, and bye, Rohan.
Yeah, see you.
See you tomorrow, right?
Yep. Sign.
Wait, how is Toga gonna work?
How is Toga gonna work?
It's like
the math club?
Yeah.
The link is posted on Canvas, so you could just go there to have it, to find it, yeah. All right, then I'm gonna dip, so see you guys.
I go to like challenges and then I find 2-pointer winner.
2.1. I guess there's no winner today because no one's actually doing it, but
okay.
Yeah, so if you solve it, actually just feel free to send me that you solved it and then I'll give you the winner flag.
Seems legit. Okay.
Yeah.
Bye.
All right. See you.